Okay, we're live now with the second part of the morning for the first day of the workshop of architectural machines. Please let me know if you have any questions about the slides that I show you this morning. It was just to, like I said, set a little bit the overall topic for the workshop. But in case you have questions, please don't mind asking. And at any moment, this is for the participants, please don't mind also interrupting me, like opening up the microphone and telling me something. You might try with the chat first, but I'm not really fast in responding to the chat. I admit that myself. So if you really need some explanation about some parts that we're doing, or if you get lost, please really don't mind interrupting me, even if I'm talking. Just let yourself be heard, and I will stop and go back to the topic. For the auditors, please don't do that. We're going to have a round of questions at the end after 5 p.m. with you. Like it's going to be half an hour, more or less, if you have any questions. So I will stop with you after we close the streaming at 5. First of all, did everybody manage to install the plugins and the rest of the material, or did any of you encounter any problem?
No problem.
Okay.
No problem.
No.
I don't have any problem either.
Great.
No any problem.
Okay. Just in case somebody had any kind of problem or is experiencing any kind of problem, like I said, don't mind interrupting me and asking. This, like I told you, this is my first remote kind of workshop. I'm really not used to do this. I'm really so used to the dynamics of classroom in presence, where you can actually feel the classroom. So sometimes you might have the feeling that I'm droning away. It's just that it's very hard to have the feeling of your response, of your attention when doing this in this way. But I will try my best to keep your attention high. So just to start with, if you have your material downloaded, just go to the folder inside the material folder. So you have a bunch of subfolders and some Grasshopper definitions and a Rhino file to start with. So let's open up Rhino Grasshopper if you haven't done so already, and open up the 3DM file, the collision test dummies file. And in Grasshopper, we're going to open the first one, the 00_0, the orientation principle. So let me have a look around before we start. So in each of the definitions here in this position on the top left, there is the Rhino file that you should reference with the definition. So in case something is not working in the definition, first of all, check if the correct Rhino file is open. Here in the Rhino file, there are some layers that are switched off. So bring up the layer panel and switch on the components layer. So now you should see the basic geometry of the components. So how does the basic principle with which we are working with, how does it work? So when doing assemblages, what you do is basically you put an object and you stick it in some parts of another object. And that's the very elementary operation. So to ensure that the basic command that you use is an orient command. So you basically orient an object on top of another object. When you have to define a position in space, what you need in terms of data, it's just a simple point. But you have to place an object. A simple point is not enough, because then if you think about an object in space and you define just a point, well, the object can be in that position, but you don't know the orientation of the object. Because the object can be in that position, but in infinite possible rotation around that point. So in order to define the precise position and orientation of an object in space, what you need is to define a plane, a coordinate system. In Rhino, the object that corresponds to a coordinate system is a plane, which is not really a geometry, but much more akin to a real user coordinate system. In Grasshopper, these objects are called planes, but remember, they are coordinate systems. So in order to define how an object goes together with another object, you have to predefine the planes that you use for orientation. And you define two kinds of planes, because an object can be both the object that goes together with the other object, or it could receive another object onto itself. It can be another instance of the same object or two different objects that you stick together. So it's a sort of really a plug and socket kind of thing, except it's not that you have a necessarily physically shaped plugs and physically shaped sockets. It's just the concept that there is one plane that acts as the plug and another plane which has corresponding characteristics that acts as a socket. So when you have to plug things, you do this sort of things. So how do this work in practice? So in the case of the file, I have defined the two very simple geometries. And around these geometries, you can see there are some polylines shaped like an L, just like this one or this one's. These L-shaped polyline are the geometrical object that you're going to use to put a placeholder for a plane. Because actually the polyline acts as placeholder for 3 points. So if you look at the directions of this object, now let me go to, well, what happened? Sorry. Okay, let's see in wireframe mode, but let's see it in this object. So if I look at the direction of, for example, this polyline, you see the polyline has to be drawn with a specific sequence for the points. So if you look at this is the first point, the center is the second point, and this one is the third point. So the points have to be perpendicular to each other, but you start with the point that is in place for the x-axis, then the origin, then the point that is in place for the y-axis. So you know in this case that the z-axis is going outward with respect to the object, okay, because of the orientation of the coordinate system. Are you familiar with the right-hand rule to determine the position of a vector when you have two perpendicular vectors? Or are you familiar with vector geometry enough to understand what is a cross product? Please say yes or no.
Yes.
Yes.
Okay. So you know that if the two vectors are shaped like that, the cross product is going outward from the object. But if I keep this vector like this and I reverse this one, the z vector will go inward, right? And that's exactly the principle, which is if I want this object in this colored area, which is actually represented by this L-shaped polyline in the center, to go exactly in the correspondence of this other colored area. So the object has been designed to be modular, so that this yellow square is exactly shaped at this pink square. I have to place a sender plane here, which is shaped like this with the Z outward. And if you ever use the orient, you know that to do an orientation, the object will be transferred from this plane to the corresponding plane. But if I use another outward plane in here, this object will stay inside the other, because the planes will be facing exactly the same direction. So the trick is, for every position, you have a sender and a receiver plane. The sender plane points with the Z outward. The receiver plane is the same, except it's flipped around the Y-axis. So let's see this in practice. So this is our sender component, the one that is highlighted. These are all his potential sender handles, and we selected just this one for practicity. And then you can select with this selector in which handle you want to go into the target object, into the receiver object. So we'll call this one the one that moves towards the other, the sender object, and the one that receives the object, the receiving object. You can also decide if the receiving handle admits some rotation. Okay, we'll look at the rotation a little bit later. So let's animate this. So if you just scroll the slider, you will see the object exactly moving into position. Right? Since you have to just imagine that from here, you always have like an arrow which represents the Z-axis that needs to plug into the Z-axis that goes inward in here. This kind of plug socket movement that I was talking about. So this is the idea by which you orient object. You just start with a plane in a specific position, and then you design a plane if let's say this attachment should be compatible. You should design them so that the handles, the orientation, and the position end up being in the same place. Since this figure is a square, it doesn't matter if I plug at 0 degrees, at 90 degrees, at 180 degrees, because being a square, if I rotate 90 degrees, the component will still be compatible. So if you try to move the rotation selector, so the first rotation was 0 degrees. If I move to 90 degrees, you see that the object is oriented in the same position, but rotated 90 degrees with respect to the original orientation of the receiving handle. If it's a square, I can also go to 180 degrees. The other rotation would be exactly equal to 0 because it's going to be, not going to be equal to 90 if the object is not symmetric. I just didn't put it here, but we can also put add the 270 and you see what happens. But the point being that you select what we will call a sender handle. You select it's called the receiving handle. And then you have to choose which object, which sender handle goes into which object, into which receiving handle. So that's the basic, it's sort of like a Lego system, you can think about it. Okay, you got 2 Lego pieces. You have to pick up the pieces that one is going into the other. And then you have to pick up where the first object is going to click into the second. Except in the Lego pieces, all the handles, sending and receiving, are already predefined and placed in specific positions. When designing the components, you will have to design also the specific positions of these handles. And all of the handles are going to be potentially both senders and receivers. This is going to be up to you to design them in a way that you make them compatible when the shapes are going together. So you'll need also to do some tests for the design of the component so that you know which one is compatible with which. In this specific case, if you look at the two components, this second component, they are starting from a very simple modular principle, which is they start from a box and then there are some more boxes. It's just that this one has some slight variation in the ends. So this yellow plain yellow square here is basically compatible with every possible handle in this other object. So if we change the destination, we see where the object ends up to, right? And we see that they are all compatible because they come from exactly the same shape. And for all of them, since they are square, all of them support this kind of possible rotations, right? But if I look at the faces at the edges of this one, this is not a square anymore. This is different proportions. It's actually 45 degrees skewed in the horizontal and in the vertical direction, respectively. So these two handles are not compatible neither with this yellow one, nor with any of the other objects, but they are compatible with themselves. So you will be able also to define a specific type for the connectors, or handles as we call them. So this square kind of handle can all be assigned to a specific type, and you can call it type 0, for instance. So all of the squares, you can define them as handles of type 0. So the system will know that they are cross-compatible with each other. And these two, since they are compatible with each other, but not with all the other ones, you can define them as handles of type 1, for instance. And you can go on and define as many types as you want. The system will be able to distinguish the type of handle and allow you to connect handles that are only the same type with each other. So an object can also connect with itself. So if you want, you can make the object connect with itself. Now, this is just a very, very simple visualization of the basic principle. But right now, what we will do is to start building up our first components and objects, because then you have to understand a few things that the objects are going to contain in terms of data that is going to be useful both for the assemblage process and for what comes next. Any question?
No, that's good.
Okay.
All good.
Great, perfect, thanks. You will see also that we are going to work with very, again, like I said, very simple objects, but we'll also give you some design pointers that come a little bit from what somebody else has done and out of experience. And you will notice, some of you at least will notice a very strong similarity with a plugin that's called WASP and was developed by Andrea Rossi. And there are a lot of things that WASP already does, but there are a few things that the WASP doesn't do yet. So I have to say, naturally, kudos to Andrea for developing WASP, which is a very good plugin, a really good plugin. And it gave me, I took a lot of ideas in terms of what WASP does, but then I decided to develop an entirely different project. Also because it's not in Python, it's in C#, because I'm more familiar with the language. So that's the need for the library. It's essentially a container for custom data types so that you can pass them from one component to the other. I plan one day to transform this into a proper plugin, but until then, things are pretty much in evolution. So this is the reason why it comes to you in this very raw form. So there are like custom C# components and the library, and it's not really properly packaged yet. Because I still need to iron out some kinks, and actually I wanted to have feedbacks from those of you at least that are more accustomed with this kind of workflow, because we're going to do things a little bit differently. And maybe there are things that can be done to make it more intuitive, more powerful, or just ideas to enrich it. And I will be very curious to hear them. So moving on.
Excuse me, just a question.
Yeah, sure.
Is it possible to have access to the DLL source?
Yes, I plan to do that, but I didn't plan to do it right now. But if you want, I can send you the Visual Studio project for that.
Okay, yeah. It's just to see how it looks like and just to learn.
Sure. No problem. I just for you in the workshop, for everybody in the workshop who is curious about it, yes, I can send it, no problem. It's just that I wanted to wait a little bit before divulging. I mean, I'm all for distributing this as an open source, but later, because then I want to polish it a little bit more. So I have no problem sharing it with you guys as long as you promise to keep it for yourself and personal study. Because in a later moment, it will definitely be shared. Just I'm not confident sharing it yet. Okay. But sure, I'm going to send that. Actually, I'm going to send it to everyone. So if you're curious to look at it, and if you have confidence with C#, and you think it can be improved, yeah, I'm also open to take pointers from you guys. So let's move on to the 00_1, the component setup definition. You can keep this. All the definition up to the 05 work with the same Rhino file. So when you open the definition, you will actually see a prompt asking you to locate assemblies.dll. But the thing that if you do it as soon as you open the file, Grasshopper should be able to do the correct to point all the components in the correct direction for it. I don't think you have to do it component by component. So, okay. Let's start from the basics. So the first thing that you need to do in terms of bringing your design in Grasshopper so that it's going to work with the system for the assemblies is to tell the systems to build the handles. So for sure, for any handle, you're going to need the L-shaped polyline. Just remember the sequence of points for each of them. So if I explode them and just put a point list just to see the order of the points. Yeah, sorry, I need to place the points, of course. Well, a little bit too much. Yeah, better. So you see the order of the points for each of the handles. Okay, 0, 1, 2. Yeah, maybe it's too much, even 1. Okay, now we go. 0, 1, 2, 0, 1, 2, 0, 1, 2. So you see how the polylines were actually drawn in the file. So these polylines are converted into a plane inside this component. And for each of the polyline, you have to specify also all the possible rotations in case this one becomes, or this one, each of them becomes or works as a receiving handle. So all the polylines define, first of all, that in this position they work as a sender handle, and the sender handle has like probably you've lost me for a second there, I think. It's because of the rig I'm using for the microphone, because the computer microphone is so close to the fan, and the fan is like an airplane jet right now. So since I don't want you to like hear me like I'm attached to the outside of an airplane, I had to rig the phone to work as a microphone. So yeah. Again, if you see anything happen or you stop hearing me for any reason, just make some noise, do something, and then I realize that I have to. So again, each polyline works as a sender handle, so the component can be taken and placed into someone else, or a receiving handle, so it's ready to take somebody else to come in and be attached to itself. In this latter case, each of the handle can have as many rotation as you want. So to do that with the correct data structure, each polyline should go as a separate branch. So, wow. So each polyline should be grafted to go as a separate branch, and then with entwine, this component here, you can place for each of the polylines. So remember, if you have we have 3 polylines in this case. If you have more than 3 or less than 3, you have to change the number of branches that you're putting in here. With a zoomable interface, you can add or remove branches to this one. Just remember, you should have an equal number of branches here to the number of polylines that you place in here. So even if you have just one rotation, just place a single number, but still use this entwine component to build up the set of rotations. Then you have to define the type. So in this case, you will see that the first and the third polyline are of type 0, and the middle one is of type 1. Because of what I was saying earlier, so you will see that all the handles in this other component are of type 1, because they are all compatible and they basically share the same shape. But the shape thing is more up to you in terms of design. The system, in reality, doesn't know anything about the geometry of the component in terms of recognizing the handle. It's up to you to design them so that when the 2 planes are coming together, the geometry is coherent and it sticks, and you create, actually, you can use it to create certain effects. But the geometry coherence is actually a very important thing for using the assemblage as a computing instrument later. So if the geometry is not compatible, so let's say that you define this as type 1, and in the other component, type 1 corresponds to a circle, then or a cylindrical thing, then, well, you have like a cylinder going into a square, and it doesn't look good, okay? Long story short. But, well, and the other thing that's really not used right now, and actually I should have 3 values instead of 2, it's the weight of the handle. Now, the weight of the handle right now, it's an unused parameter. It's for something that I had in mind to develop later. Still, it's up to you if you want to put it or not. You can put any values in here because for now it's not considered. Because it's the idea of the weight of the handles is that when they form, an assemblage, you have a knowledge of which handle is connecting to who. And the weight could be used to simulate the distribution of data. So when you distribute data in a graph, you watch what is called the weight of each connection. And according to each connection, you distribute part of the value somewhere and part of the value somewhere else. So think of a bifurcation. Think of exactly to a tree branch, for instance. So the branch that's closer to the trunk is larger, and the two branches that are the farthest are becoming thinner and thinner, right? That's because the flow divides from the larger branch into the two smaller branches. And it divides proportionally according to the section of the two smaller branches, right? So the weights should have, in theory, more or less the same role. They represent a sort of, let's say, abstract kind of section for the flow of data to go through. The bigger the weight, the larger the section. So if you want to distribute the data or see how a certain data flows through the system, then you input an amount of data in a portion of the graph, and then you see how it distributes around. But for the moment, they are unused. This is one of the things that I had in mind to develop later. I didn't know if it was time to do it for the workshop, but definitely is going to get done later. But yeah, at this moment, you can really put whatever value you want. It doesn't matter. So what comes out of here is a custom type called the assemblage handle that is then managed by the other component, which is the object, the builder of the assembly object. The same thing happens for the other objects. So we build the handles. In this case, we have 4 handles, so I'm having 4 branches. In this case, are all of the same type, so they are all admitting the same kind of rotation. In the first one, as you noticed, these handles at the extremities, they can only work with an angle of 0 or 180. Because if I rotate, since it's not a square anymore, if I rotate it 90 degrees, the edge and the vertices do not coincide anymore. Because there is one side that is longer than the other. So the only symmetry for connection is 0 or 180 degrees. So after you build the handle, they go into this other component that contains all the other data to build an assembly object, which is the basic building block we'll be working with. So first of all, you have to input a mesh, which is this one. This mesh is going to be used to test the assemblage for collisions, to make sure that when you place objects, they don't stick into the other object that you already assembled, or they don't stick into themselves. So this one, doesn't have to be the exact high resolution geometry or contain all the details. It's more of a wrap-up of the things that you don't want to get interfered with. So think about, for instance, Christo Jabachev wrapping up the Reichstag in Berlin. Okay, all the ornaments of the Reichstag are not there, but you have a decent low resolution approximate of a volume. So the amount of approximation is really up to you, but the lower the better. I mean, the more low poly you can stay, the better, because it makes the system faster, which means the collision check takes less to perform. So in this case, I just use the dummy, but you can then, let's say, chisel your geometry inside this space to make it, more intricate, more complicated. But again, you don't need to add too much detail to the part. We will see with the design input how something works in a certain way and other things really do not work. Because it's not just the part in itself. Again, it's more the idea of what a part does in a larger assemblage. So, first of all, the low poly mesh. that should be, let's say, sort of a wrap-up of the boundaries of the object that you want. Then you have a name. This name is an identifier to recognize what object are you talking about when you write the rules for assemblage. This can be anything you want. Just avoid some special characters that are used in the rules. So do not put any vertical slash. Do not use the equal. Do not use the smaller than, and do not use the percentage. These are the special characters that you have to avoid putting in the name. Except for this, you can use whatever you want in the name. My suggestion is please do not use spaces. It might. I've never tested if it works with spaces or not, but just to stay on the safe side, do not put spaces in the name. Then there is an ID, but actually the ID here, yeah, that's one of the things that I need to adjust. You can put the ID here. In reality, the ID will be assigned according to the order in which you give the object to the system. So the first object in the list will have ID 0, the other ID 1. So, I mean, you have to assign a value here. That's something that I haven't completely fixed yet. But just remember, you have to put an ID here, but the real ID would be identified by the system. You identify it by the name of the object. There is, again, a weight, which more or less has the same scope, the same purpose of the weight of the handles, except this one is for the object. And then it allows you to, maybe we will use the weight of the object, because then you can compute a certain things. So the weight can be related to the density of the object, for instance, or the amount of space, or let's say the shape per volume percentage or something like that, or anything that you can think of that can be expressed in a sort of a number, and that you can associate to the object, because then you have this distribution of numbers, and then you can look at your surrounding and see, okay, what is the overall weight in the volume of my neighborhood? And then according to that, you can perform some actions or decide to not perform. But it's all to make the system aware of distribution of values. The other is the direction. So in this case, it's an X vector. This is just a general vector, because then you will see that we can work also with a vector field. So the object can be chosen according to how close is its orientation to the vector field. So you can decide a field of orientations in your volume for the growth, and the system can pick the rule that decides the component that is which direction is closer to the direction of the field in that position. And then we have an orientation plane, which in this case, it's automatically placed in the centroid of the geometry. One important thing that I forgot to mention about the geometry, the collision geometry, this one should be a closed mesh. It cannot be an open mesh. So this is very, very important, because to perform collision, the system uses a command that basically checks if something is inside or outside the mesh. So if you use an open mesh, this inside-outside distinction it's meaningless. So you won't be able to perform collision, or the collision result might be strange, unpredictable. So very, very important thing, this mesh should be a closed mesh. The best thing is to verify that the mesh is not just closed, but properly welded, watertight, non-manifold, etc. Since we are dealing with, it doesn't have to be complicated. It's going to be very, very, very simple. It's not so hard to perform this check beforehand, but still, I invite you to do it. So the reference plane that we are using will have at least a couple of purposes, but then any information can be used for any purpose that comes into your mind. It's just there and you can access it and then you can use it as a resource. But the two main purposes for this is the plane is then, all of this information travels with every object that we place in the assemblage. So in the end, the assemblage will be a set of information with a set of meshes, a set of planes oriented in a certain position and rotation in space, and all the other collateral information that we are storing here. So the plane will store the position and orientation. So if you want to orient your final geometry, you can do so after the assemblage is finished. And this makes the system faster because you don't have to embed all the complex geometry in the object because you don't need it. You embed in here only the information that is relevant while the assemblage is going on. The final geometry, you can orient it at the end because then it's the finalization of one thing and then you want to see how the geometry looks like in the assemblage. This makes also modifying the geometry faster because then you can, or make alternatives faster, because then with the same bounding, the same collision geometry, you can have several versions of a final geometry to orient. And then you can maybe choose which version you want to orient according to how the reference plane landed in the assemblage. If it landed horizontally, you can decide to place a certain internal geometry. If it landed vertically, you can selectively decide to place another kind of final geometry, or up to you to know. But you can start to see what's the flexibility. And the plane also allows you to detect the orientation of the object. And also determine if you want to look above or below, left or right, because having a plane lets you see if there's something in the positive z direction or the negative z direction of the object. And then again, it's an information that you can use to decide some selective action afterwards. But in the part in itself, this is still a generic property, but it enables capacities when the component, when the single part is then oriented in the assemblage. Then, according to how the object relates with its neighbors, you can decide to take some actions. So this is how we build one object and the other object. So when you place the object, you place them in a merge component. The order in which you place them in the merge component, this is the order that will determine the real object ID in the system. Okay, because I realized that if you decide the ID here, but then you decide to plug this second, the system was acting funny. So, and I discovered this like yesterday evening or maybe early this morning. So I said, okay, let's the system decide. It doesn't matter because then you will recognize the type of object. It doesn't matter that much. It's more important that when you see the rules or when you have to write, if you want to write some custom rules, you recognize the object by name. The interesting thing is that probably you won't have to write any rules at all. You just have to pick from something and then maybe compose the sequence that you want. But we'll see that in the next definition, and maybe we're going to do that this afternoon. I'm going to just end up with this deconstruction components. These are for analysis, and then with a few minutes left, if you have any questions, I'll leave it for that. So these are quite straightforward. So the deconstruct assembly object allows you to pick into an assembly object and extract all of the characteristics, the mesh, the handles, the reference plane, the weight. There is also another value, which is the scalar, which is assigned internally. That was another thing for this sort of post-assemblage operation that is not implemented yet. And the direction vector. So, for instance, you can use this deconstruct at the end of an assemblage to retrieve the information for all the assembly objects. Because at the end of an assemblage, you're going to have as an output a list of assembly objects. Inside the assembly object and inside the handles, so if we go to the handle, there's also a deconstruct handle. The handle actually contains a lot more information than the one that you build it with. So you have the sender plane, the receiving planes. So for each rotation, a new receiving plane is built. The rotation in degrees that you have, that this handles admits. The weight, that it's not an unused parameter. And these are the type. It's the type that you assign. This one, HO and NH, these are the interesting ones that you want to use for analysis. So HO is the handle occupancy. So if the handle has been connected to some other component, it will take the number in the assemblies list, the index of that other component. Otherwise, if the handle is not occupied, the value is going to be -1. So after an assemblage, if you want to test, okay, how many free handles have I left? Which free handles have I left? I'm going to decompose the component, decompose the handles, and look for any handle with the value -1. So I can pick them up and say, okay, these are all the free handles. Maybe I can add a geometry to them or do something else. NH, it's the index of the neighbor handle. Because other than to which component am I connected, I want to know to which handle of that component I'm connected to. So think about people holding hands. I'm holding hand with somebody to my left and to my right, but am I holding his left or his right hand? I want to know. And this tells me if I'm holding the person. Let's say I'm looking at the handles of my right hand. I know that I'm holding hand with person number 35, let's say, and I want to know if I'm holding his left or right. This neighbor handle index allows me to know which handle in the other component am I connected with. There's another value that handle occupancy can take, which is -2, in case the handle is occluded. Occluded means that during the assemblage process, you can have objects that are placed physically in front of the handle. So the handle is not really connected to anything, but it's impossible physically to connect anything else to it. So this means that the handle is not occupied, it's still free, but it's occluded because even if it's free, I cannot place anything into it. So we have this status, which is -1 free, -2 means that the handle is occluded. Any other number from 0 to n is the index of the object the handle will be connected to. We'll take this up again when we start doing our first assemblage. So we analyze the post-assemblage data. But this is everything that's encapsulated in here. So all of these data, like a handle occupancy and neighbor handle, it's managed internally by the system. So you don't have to define it when you define the handle. You just have to define its geometric properties. And let's say at some point, the weight will have some significance, not right now. Same thing with the object. And then there are certain parameters that are managed internally, and they make sense once you have the assemblage per se. Okay, so I'm going to stop here for the morning. If you have any questions, please.
Yeah, just with the neighbor handle.
Yeah.
So which values are there? Is it -1 means left or right, or how does it work?
-1 is automatically in place when the handle occupancy is to -1. So if the handle is free, you have no neighbor component, so it's -1.
Oh, it's just yes or no. So it's
yes, the neighbor handle, actually, when the handle is occupied, is the index of the handle of the other component. So let me just let me explain it this way. So here, each polyline goes into a branch, right? First 0, 1, 2. So 0 is corresponding to handle index 0, 1 to handle index 1, 2 to handle index 2. So this component has 3 handles indexed 0, 1, 2 that are exactly, if you look at the origin of these curves and let's say, let's transform them into planes. And look at another of this. Yeah, the number are little, yeah, so 0 is this handle here, 1 is this handle here, 2 is this handle here, okay? So the index of the handle depends on the order in which you feed the polylines to the component when you build the handle. The other component here has 4 handles, so the index for his handles are going to be from 0 to 3. So when you, in neighbor handle, you're going to have one of these values. So if this one is the neighbor component to the other, his neighbor handle index will go from 0 to 2. But if that guy is the one attached to the one I'm looking at, so this one is the neighbor, and I'm looking at some connections, I'm going to have an index of one of his handles. So it's going to be an index from 0 to 4. So the index that you find in neighbor handle is the index of the handle in the other component, the one that is connected to the one I'm looking at. Is that clear?
Yeah, thanks.
No problem. Any other questions?
I had, sorry, I had another
Yeah, no problem, no problem.
I saw in the chat some of you guys were discussing an error, and I think I have the same. I don't know if it's
some
it's a
range
thing with the
modules.
version. Yes.
Wait.
But the outputs are okay. It's just an error message.
The component is orange, by the way. Okay. Yeah. Sorry, I missed the chat completely. My fault.
But the outputs are okay.
Yeah, don't worry. The culture token, culture neutral public token, that's a harmless error message. Something that it really has to do with different versions of Rhino against which the library is compiled. So I don't have any precise idea on how to make it go away, but it really is harmless. I mean, it doesn't compromise the system. It's just a warning. But since I'm not,
all the 4 components.
It's just annoying. It's just annoying, but it doesn't do any harm to. So. Yeah, I know. Maybe because probably it comes up when you have a more recent version than the ones that I compile it against with too. But on the other hand, to have maximum compatibility, you have to try to compile it for the lowest possible version so that it's retro compatible.
I have SR13 and I have the same problem.
Well.
I have a lower version. I think you developed it in 25, right?
Yeah.
Yeah, I have 13 and I seem to have the same problem at the output.
But you have output null from where?
Sorry, come again?
Where is your null output from?
Okay, it says error CS1705 assemblage version 1.00 public key token null uses Rhino common version 6.25.2011.
Yeah, but okay, that's the out. That's the message. Mm-hmm. But do you have errors in the actual output? I mean, is there some part of the definition that doesn't work?
Yeah, I mean, I'm just getting null outputs at the end. That's what I was saying.
In the out of here?
Yeah.
Oh, because I think, yeah, I think that the problem is that having a, because you have a version 6.17. Somebody has the version 6.17. Rhino Common version 6.17, right? Is that the same to you? You have a Rhino Common that is lower than 6.26 or 6.25?
The 13 one. I'll just check quickly.
Yeah, because if you have
6.13.
Yeah, that's the problem. But when you tested the DLL, you didn't have any problem?
No, that time it worked fine.
That's very weird, because this kind of error is due to the DLL. But just the deconstruct that gives you an error, or also the construct object?
As well, I have all the null outputs.
Ah, okay, yeah, because it makes sense that none of the component work. Because that is strange, because that should be a problem with the DLL. Yeah, the thing is, if you have a lower Rhino Common version, I have to recompile the DLL for your version.
Right.
So yeah, but I need you to send me some files, and I need to check which files you need to send me. So I will send an email to everyone just asking who has the Rhino SR lower than 25 to send me, or yeah, the lowest one. Actually, I think the lowest that you have is 6.17. So anybody who has 6.17, you're welcome to send me your Rhino Common and some other files. So I will tell you specifically which files and how to send them to me. So we'll try to compile it before the afternoon or right after.
Yeah.
So that you can work with it. Or otherwise, some like Alexander suggested, there's also the SR27 evaluation. That would solve the thing without having me recompiling stuff. But
yeah, I might as well just install it then.
Yeah, if you can install the evaluation, that will be definitely a lot better, because it will save me.
Yeah, I'll try to do it right away. It's downloading, and then if it doesn't, then I'll write back to you. Okay.
Let me know if you manage to download the thing. Otherwise, in case you don't make it, I will try to compile, but I don't think I can do it before the afternoon session in this case. All right.
All right.
Anything else? Sorry about that. Anything else? Because otherwise I will say that we're done for the morning, and I'll see you again at 2, right?
Yeah.
Great.
Thank you.
Okay.
Thanks.
See you this afternoon. See you in an hour, actually.
Thank you. Bye.
See you.
Bye.